right, let's dive into the microscopic battlefield that's raging inside us all the time. Today, we're looking at one of medicine's absolute game changers, antibiotics. We're going to break down how these amazing drugs manage to pull off what seems like an impossible mission. And this really is the core problem, right? Think about it. Bacteria are living things. They're cells, just like our own cells. So how on earth do you create a weapon, a kind of magic bullet, that can hunt down and wipe out these tiny invaders, but leave our own trillions of cells completely untouched? Well, the secret is all about exploiting their weaknesses.
And that brings us to this incredibly powerful idea, the selective strike. This isn't about just dropping a bomb and hoping for the best. No, this is precision warfare. It's about finding what makes the enemy unique and hitting them right there.
The fancy scientific name for this is selective toxicity. But really, it's the holy grail for anyone designing these drugs. The entire goal is to find something, anything at all, that a bacterial cell has or does that our cells don't. And once you find that target, that's where you aim all your firepower.
This right here is basically our intelligence report on the enemy. It shows the key differences between our cells, which are called eukaryotic, and the much simpler bacterial cells, which are prokaryotic. And look at these differences. They've got a unique kind of body armor. Their little protein factories are built differently. They have a totally separate supply chain for key nutrients, and they even use different tools to copy their own blueprints. Every single one of these differences is a potential bullseye.
So here's our game plan for this explainer. We're going to walk through these sabotage tactics one by one. We'll start by cracking their armor, then we'll move inside to shut down their factories, scramble their genetic blueprints, and cut off their fuel supply. And finally, we'll talk about the scary part, how the enemy is fighting back in what's become a never-ending war. Okay, first up, we go straight for the armor. Just like any good fortress, a bacterium has a tough outer wall to protect it. But it turns out that armor is also one of its biggest weaknesses. This wall is made of this really unique mesh-like material called peptidoglycan. Now, here's the crucial part. Our cells don't have this at all. We have soft, flexible membranes, but not this rigid outer wall. And that makes it the perfect target. If you can break that wall, the bacteria literally just falls apart. So how do we do it? With maybe the most famous antibiotic family ever, beta-lactams, which includes things like penicillin and amoxicillin. Their secret is pure deception. They're shaped to look almost exactly like one of the building blocks of that bacterial wall. So the enzyme that builds the wall gets tricked. It grabs the antibiotic instead of the real brick. This jams up its tools, and it can't link the wall together properly. The wall gets weaker and weaker until pop. The pressure inside the cell becomes too much, and the whole thing just bursts. Okay, on to tactic number 2. If you can't break down the walls from the outside, you sabotage the machinery on the inside. Every living cell runs on proteins, and they build these proteins in tiny factories called ribosomes. And guess what? This is another huge vulnerability. Now, this is just a beautiful example of selective toxicity. We have ribosomes, and bacteria have ribosomes, but they're not built the same. You can think of it like different models of the same machine. Bacterial ribosomes are a smaller 70S model, while ours are a bigger 80S version. It seems like a tiny difference, but it's more than enough for our drugs to tell them apart. Let's take an antibiotic almost everyone's heard of, azithromycin, the Z-Pak. What it does is bind directly onto a specific part of that smaller bacterial ribosome. It acts like a plug, physically blocking the tunnel where new proteins are supposed to exit. It's literally like jamming a wrench in an assembly line. The whole factory grinds to a halt, the bacterium can't make the proteins it needs to live, and it's game over. Our next tactic is, you could say, even more insidious. Instead of just breaking the machines, why not corrupt the instruction manual itself? This strategy is all about targeting the bacteria's most precious asset, its DNA. And this is only possible because, you guessed it, the enzymes that bacteria use to read, copy, and maintain their DNA are different from the ones we use. It's the same principle all over again. We're zeroing in on those small but absolutely critical differences in their internal toolkit. A fantastic example is a class of drugs called fluoroquinolones. You might know ciprofloxacin. These drugs go after a very specific bacterial enzyme called DNA gyrase. So picture DNA as a super coiled rope. To copy it, you first have to carefully unwind it. DNA gyrase is the tool that does the unwinding. Well, these drugs block that tool. The DNA stays tangled up, it can't be copied, and if a bacterium can't copy its DNA, it can't divide and multiply. It's a biological dead end.
All right, our fourth and final major sabotage tactic. We cut the supply lines. Every living thing has these critical biochemical assembly lines, called metabolic pathways, to create essential compounds. And once again, there's a fatal difference between us and them.
It all comes down to a vitamin called folic acid. It's absolutely essential for building DNA. Now here's the kicker. We humans get our folic acid from our diet, from things like leafy green vegetables. We just absorb it. But a lot of bacteria can't do that. They have to make their own folic acid from scratch. This gives us an entire assembly line to attack that simply doesn't exist in our own cells. It's their Achilles heel.
And this slide just shows the beautiful trickery involved. To start making folic acid, a bacterium needs a molecule called PABA. That's on the left. Now look to the right. That's a sulfa drug. See how similar they look? The drug is a decoy. It's a PABA imposter.
So here's exactly how the heist goes down. Normally, a special bacterial enzyme grabs onto PABA to kick off the whole process. But the sulfa drug gets in there and clogs up the works. Because it looks so much like PABA, the enzyme grabs the drug by mistake. The real PABA can't get in, the assembly line is shut down, and the bacterium is starved of the folic acid it desperately needs to build its DNA.
So we've come up with all these incredibly clever ways to sabotage the bacterial machine. You'd think we'd have this won, right? Well, this isn't a one-sided fight. The enemy gets a vote. The bacterial machine isn't just sitting there. It's evolving, and it's fighting back.
And bacteria are fighting back with their own counter-sabotage plans. Some of them evolve enzymes that literally chop up and destroy our antibiotic before it can even do its job. Others change the locks. They'll actually modify the shape of the target, like the ribosome, so our drug can't bind to it anymore. And some are even clever enough to just build a whole new biochemical road to get around the roadblock we've created. It is a full-blown evolutionary arms race.
And this really leads us to the final and most sobering question of all. We have these brilliant, elegant drugs that are the product of decades of genius-level research. But bacteria, they can reproduce in 20 minutes. They can swap defensive strategies like kids' trading cards. They evolve at a blindingly fast pace, which makes you wonder, in this never-ending war, are our smartest weapons actually enough to keep up?